Logic gates are some of the fundamental building blocks of computers. So if you remember in electronics, 1 represents an on switch and 0 represents off. So in this circuit here, if we click on this user input, it turns red on and the light turns on. So a basic switch, 1 is 1, and if we turn it off, 0 is 0. So let's look at our first gate, the AND gate, and we have something called a truth table here. So when we have inputs for A and B, 0, 0, we expect the output for an AND gate to be 0, which it is. So these are 0 right now. We'll try the next step on the truth table, 0, 1. So we'll change B to 1 by clicking on it, and that still outputs 0, which is it. Then we have A 1 and B 0. So we'll turn A on and B off. That's still 0. And then the last one is 1, 1. So if we change B also to 1, we get 1, 1, 1. So this is working for the AND gate, and our truth table holds up. We look at the next one, the OR. And so either one, A or B being on, will make it 1. But in the condition where they're both off, it's off. So that's reflected right now. So 0, 0 is still 0. But if we turn on B, that goes on. If we turn on A, that makes it go on. And so if either or both are selected, it's on. Okay, so an OR is either or, and both have to be on. A and B have to be true for the result to be true. We have a NOT gate, which just negates the logic. So right now A is off and the light is on. So that reflects in the truth table. So if we turn A on, it turns the light off. So it just reverses or nots whatever the logic is. So not true is false, not false is true. The last one is the NAND gate, and at 0, 0, it turns on 1, so that's already there. If we select B as 1, that's going to be 1. And if we select A as 1, that'll be 1. And if we select both, we expect that to turn the light off, which it does. So reflected in the truth table, 0 here. So this is important because we're going to build some other chips based on this, and we can actually use the NAND gate to build some of the other gates. So if we go back up and we look at the NOT gate, we see if we put a NAND in and we just take the input for our input here and we send it to both A and B of the NAND gate, we end up with an equivalent NOT, which a NAND is really just an AND followed by a NOT. So that works if we just put an AND in and connect the inputs this way. We essentially have a NOT gate. We can also create an AND. Okay, so the only way to get AND, we'll go through the truth table, 0, 0, 0, 1, nothing, 1, 0, nothing, but A and B. Okay, so if we hook up two NAND gates in this way, we can essentially make an AND. We can also do the same thing if we take out this second NAND. You might recognize that this looks awfully familiar from up here. So that's actually a NOT. So if I click on this gate and take it out, and I actually put a NOT in here, there's another way of creating an AND gate, and you can run through all the different scenarios, and that works the same. So, but if you're just building it out of NAND gates, you can basically take that and put it in here. And then the OR gate, we can also do with NAND gates. So recognize again here, we're just taking A, inverting the input. So this is really just an inverter, but we're implementing it using a NAND. Same thing with the input for B, filtering it into another NAND And then, of course, it's going to knot one more time before it comes out. So the way that operates 0, 0 is 0, 0, 1. Turns it on, 1. 1, 0 is 1, and 1, 1. So even though we're using NAND gates, we have the equivalent of an OR gate. Okay, so now let's look at our NAND to Tetris hardware simulator. So it should be under Tools. And you do need Java for this to work. So I'm just going to run the hardware simulator .bat. And I'm going to back up a little bit in here and go back to projects. And we're looking at project 1. And so first thing I'm going to do is load a chip, and what I'm going to do is load in a built-in chip, and I'm going to pick the NAND gate because we're given that. Okay, so they've created a NAND gate for us that works. And again, if we look at our truth table for NAND, what we can do is come over here for our A and B values and put in. Let me move this so we can see. 0, 0 is already 1. If I change B to 1, notice up here the calculator shows up because we have one of the values that's changed here. So I'm going to hit the calculator so it calculates the output, and we still have 1. And if we go back to 0, and 1 here, we would expect that to be pretty much the same. And then if we do 1, 1, we should get 0. So let's change that. 1, 1, here, enter, and of course we do get 0. Okay, so that's the built-in NAND gate when we can depend on it to operate that way. But what we're supposed to do is load a chip, and we're going to go back to the projects, and we're looking at project 1 folder. And the first one I want to implement was the NOT, because the NOT seemed pretty easy to implement. So I'm going to load that in. Now this is read only, so you're also going to have to open that same file in Notepad or whatever your editor you want to open it in. And so we're going to edit the code right here in Notepad. And so it says put your code here. So we're going to go in, and the only gate we can use is the NAND gate. So I'm going to call NAND. Okay. And if there is a guide to this that you can look at, and so according to the guide, you know, again, we're using A as input. So I'm going to say, well, our input is defined here in. So the A is the input to the NAND gate. So A is going to be equal to the input of our NOT. And B is the same thing. B is going to be equal to the input of our NOT. Okay. And our output's defined as out. So I'm just going to say output is equal to out. And we have to put a semicolon here. So that'll do that. We'll save this. Okay, and if we reload our chip over here as a NOT, we can verify our read-only view here that it loaded the code we changed here. And so now we can test our NOT. So 0 is 1, and let's put in 1, and we'll test that, and it's 0. Now there's another way to do this, because we can also load, there's a test script built in to kind of automatically test this for you. So I'm going to load the NOT test script, and it will load over here. And just as a quick way to check whether we got this code right or not, we can either step through it using this single step, or we can just run it. So I'm going to go ahead and click run, and notice it's running through all the script. And then it will come back down here and say end of script, it completed successfully. And so we know we're good to go there, right? So let's try our next chip is the NOT. No, we just did the NOT. Let's see, we need the AND. So again, you can refer back to the first part of the video where we used two different NANDs here. So we're going to put the code here, and I'm going to use a NAND, and this time I'm going to say, you know, our input for the AND chip is A and B. So I'm going to change this and say A equals A and B equals B, and our output is going to be equal to, I'm just going to call it N1 for node 1. Okay, and so if we go back and we look at our equivalent circuit here for the AND, okay, we're just putting input A into input A, input B into B, and NANDing that. So this would be N1 right here. We're going to take N1 and we're going to feed it into an equivalent NAND for this NOT here. Okay, so to do that we need another NAND gate. So I'll just go down here and say NAND, and we're going to take the input of that as the first input A. We're going to take N1, which is node 1, and for B we'll do the same thing. Node 1 is the input, so we're combining those inputs, and then again out is just going to be equal to the output this time, semicolon, and we should have that working. So I'll click save, and we'll go back in here and load the AND chip that we just edited, and we can verify down here that we do have the modified code. And this time I'm just going to go ahead and load the test script for AND, and we'll execute that. And after a few seconds it'll come down here and say, hey, we did it okay, it worked. That's an equivalent. Now as you start creating more chips, it gets a little bit more complex, and there's more than one possible solution. So for our AND, just like before, since we already created a NOT chip, we could take this away and put in our NOT, because we just created a NOT chip. We can use it. So we can say the input for the NOT chip is going to be equal to node 1, which was the output to from our NAND right there, and then output is just equal to output. Okay, and don't forget your semicolon. Actually, just for a second, let me forget my semicolon, and I'm going to click save, just so you can see over here when we load our AND chip, we get an error, right? It's going to say, hey, you're missing a semicolon there somewhere. So it will help you out along the way if you make errors. So I'll save this and load the chip again, and verify we have the NOT in there now. Okay, and I'll load the test script again for AND, and we'll execute that. And it gives us successful at the end, so that's another valid implementation of the AND chip. If you get an error somewhere in here and it doesn't quite work right, it will tell you in the line. It won't say it's valid. It'll give you some type of error message. So that's using the hardware simulator to create the basic building blocks or logic gates for the computer, and then in the later labs we'll use that to create more complex components in the computer system. So hopefully this helps you kind of get an idea of how to do that using this simulator.